So hello, Victor and I, we're talking about science, engineering, right? So this is probably a presentation that we've been talking about for about 3 years, something like that. So I come from a bit of a background that's similar to Victor, but this is us. So I'll just very quickly introduce my learned colleague here. He got his PhD about a month and a half ago, something like that.
Yeah.
So well done, Victor. Got a background in computational chemistry, but has also done a bunch of presentations around high-performance computing. So, learned colleague.
Martin is this part I'll read through because this is not how I know him. He's a technical architect of 25 years of experience, but how I know him, he's a science and engineer at heart. We've spent hours after hours just talking about from REST APIs to finite element methods and many other things. So. Yes.
Many things, right? So, I know Victor. I used to be at Microsoft, and he was on a kind of like a mentoring program, and we got talking, and it was just a meeting of minds, really. So, I want to just go through what my science journey is. You can tell 1990 to 1995. I'm very old, sadly. So, the reason I wanted to do this is because I wanted to say what the old days were, right? So this is the old days. Victor's much younger than I am, so therefore he knows the more modern way of doing things, right? So I did a master's degree in numerical analysis and computing. That's my thesis title. There will be a test at the end, so you please remember that, and I shall test you afterwards. But in those days, we had supercomputers. Who remembers things like Cray supercomputers and all those sort of things? The big things in a room that had halide systems in them. So if there was a fire, you had 10 seconds to get out of the room. Otherwise, you're going to destroy $10 million worth of equipment. So that's what I did my master's on. And essentially, what you did is you bought a time slice. So you put a bunch of stuff on there, you bought a time slice, and hoped that the code that you were running finished. Because if it didn't, they terminated the job, right? And that was it. You bought a time slice. Rev forward to my PhD. The reason it says incomplete is because I submitted my thesis, but my PhD supervisor didn't read it, which is a bit of a shame, but there you go, that's the life of a PhD student sometimes. So that was on a Unix workstation, so that's what that is. It took me 6 months to define the geometry that I was building to do this stuff on, and 6 months to build a mesh, and then you can see there that I did a solver as well. That was different, I had control of that. Sometimes it took 4 weeks to run my models. And basically you started off, you look at the error rate as it's coming through, you kind of hope that it's going down and getting lower and lower and lower, and then all of a sudden it will just blow up and diverge, and you're knackered and you have to start again, right? So that was my journey. So very much computational fluid dynamics. That's my background. Over to you, Victor.
Yep. So first of all, I wasn't born I just realized I wasn't born in 1995, so a bit of an age range there.
Whatever.
So my science journey, I started, my interest in science came with cartoons and books. That's Dexter's Lab. I don't know how many are familiar with Dexter's Lab. Early 2000s. Got me quite interested in science and chemistry. And I followed that in my bachelor's. I followed that also in my PhD studies. My work was more on how do we stabilize the effect of alcohol on biofuels. And actually, when I read this title early this morning, it can be taken quite differently. But yeah, so there's a wet lab component to this. So I was in the lab mixing chemicals, analyzing results, and doing all that. But there was also a computational element to it. So studying the reaction pathways. I'll get a bit later to explain why we need HPC for that. But that's been my journey. And as Martin said, I just graduated fairly recently. That's a plug to Frankenstein, Mary Shelley. I do love books, and Frankenstein is a book actually that talks a lot about chemistry and got me inspired into chemistry. So in terms of high-performance computing, one of the novel ways nowadays is with the emergence and democratization of cloud is that we can be able to do such workflows on cloud. And Microsoft Azure in particular offers this to particular services, Azure Batch and Azure Cycle Cloud. Azure Batch is more for a cloud-native solution, so you don't have to worry about job scheduling. So a typical workflow in HPC, because many people are using the supercomputer, is you would need to schedule jobs to run at a certain time, depending on the size of the job, depending on priority, and many other things. So with Batch, you don't get that flexibility, and that is good for some corporations because they don't want to worry about that. So that was the initial provision of HPC services. Then came Cycle Cloud. Cycle Cloud is more modeling the traditional high-performance computing approach as we would on a supercomputer. You can use third-party schedulers. So you can install your own scheduler. It has its own scheduler, or you can bring your own for whatever you use in your facility. And you can configure that with policies that suit you. So it models the traditional HPC scaling method.
Oh, thank you. So I'm going to talk about batch because that's my background, and Victor's going to talk more about cycle cloud. So going back to that traditional view of supercomputers and indeed the idea behind the workstation that I used, what do you do? Traditional workflow is described up there. You create a bunch of input files. Quite often that's things that are spat out of preprocessors, but you can also write them. They're very often just text files. The pool creation is about your computing resource, right? Task, obviously at some point you've got to submit something to something and something has to run because you've given it some input files and you now need to run an algorithm or something against it. Monitoring if you feel the need to do that sort of stuff. Usually I just go away and do something else. And then the output. So again, all these solvers do a similar sort of thing. You have a bunch of input files, it solves something, and it puts a bunch of output files somewhere, right? And then when you've got those output files, you need to do some form of post-processing. So specifically in my case, I'm going to talk about computational fluid dynamics. So my background, like I say, my PhD was in computational fluid dynamics. So essentially, as you can see up there, it's a very similar workflow. You have a bunch of input files. So you have a preprocessor that might be some kind of CAD package which spits out a geometry. You then have some kind of, you have to define what it is, Newtonian fluid, incompressible fluid, Reynolds numbers, viscosities, so on and so forth. Spatial discretization, as it says up there. So in other words, getting your domain and creating a mesh that is going to solve each individual location in that mesh and build up an overall view of your solution domain. Temporal, if you're doing obviously time-bound stuff as well, and so on. And you can read that yourself. Initial conditions and boundary conditions. And then the last part of that is you tell it what kind of solver you want to use. And there's a bunch of solvers in the CFD space. The one that I particularly used for this is OpenFOAM. OpenFOAM is a free to use. It's free to download CFD code. It's very good. It's very feature rich. It's as good as a lot of the commercial codes, and it's maintained by an organization that keeps adding stuff to it, right? So you can see there's block mesh. That's the thing that does the spatial discretization. And then you either do a run application or an MPI run. I'm going to talk about MPI running shortly. Because one of the other things that we're going to talk about is how you actually scale things like this to use the power of cloud computing, right? So think about that last slide where we talked about pools, compute resources, and keep that in mind. And the last one there is ParaView, which is that post-processing tool that I was talking about, and I'm going to show an example of that. And it's quite a cool bunch of diagrams.
So one of the features of Azure Cycle Cloud, as I mentioned, it's quite similar to Batch, but it allows you to deploy a HPC cluster. So you don't just, you configure the compute that you want to use, you configure the storage, and all that is done via a HPC template that you use. Also, it allows you to submit jobs using HPC schedulers. So meaning to say your VMs scale up and scale down via traffic, so via the jobs that you submit. The general structure is that you have a head node, and on that head node, the head node controls all the worker nodes. So I will save the rest of this for the demo later, but I'll elaborate more on how that works via the actual demo. On the computational chemistry workflows, that's generally what I do, what I did for my PhD as well. There's quite a lot of steps there. Don't worry too much about that. But I think I want to bring the point, why do we need compute for chemistry? That's not has been a usual field. So over there, so that I was going to ask, but I think you can skip that. That is the Schrödinger equation. That's the time-independent Schrödinger equation, and that really is...
You should have put that out to the crowd. I'm sure they'd have...
I think they would have got it, yeah. Sorry, that's my bad, yeah. And so it governs energy and everything at a quantum level. The reason why we need HPC is because that particular equation, the term highlighted in red, is your potential energy. The potential energy of an electron is very hard to calculate for an atom such as the one shown there because there's 3 electrons. Depending on the position that it's on, it interacts with the other electrons. So a little bit of integration from maths. If it was just one electron, you can solve it via integration quite easily. But because there are 3 of them and they're dependent on each other, you cannot separate your variables and it becomes very complex to solve analytically. So that's why we need numerical methods. That's why we need algorithms to solve. Just an interesting note is the only atom that you can solve analytically for the Schrödinger equation would be hydrogen, because it just has the one. But that was just a bit of an intro, why we need HPC there.
So I'm just going to very quickly jump in there and say that's a very, very interesting equation. I deal with computational fluid dynamics, Navier-Stokes equations, and that sort of stuff, and which are way more complex than that, right? So he did really simple stuff. That's what I'm kind of trying to imply. He did the simple stuff.
Yeah.
Right. So we were talking about compute and all that sort of stuff, and you can imagine that if you've got a very, very complex domain, you don't want just one machine running it, right? So there's this concept of MPI, message passing interface, the idea of being able to split up your domain and move it around, right? And have it being processed on multiple nodes. So going back to what Victor was saying, and your demo shows a lot of nodes, it's the opportunity to split the workload. But if you do that, you need something behind the scenes that allows you to bring all that stuff back together. So how does that sort of work in practice? So imagine that's a domain. So that's driven cavity example, for example. You decompose that domain into multiple domains, right? That's fantastic, that's good. You then create a gap between them, essentially, but you need a bunch of cells that sit on the outside of that, which are going to do the passing of the information from one domain to the other. So if you can imagine that what you're doing here is you're going, okay, I'm going to solve that, say, yellow domain right there. When I've solved that yellow domain, the boundary of that domain, I'm going to pass the information to the blue domain. What you typically do is you solve for a time-bound area, and you pass time step -1 between the two, because essentially you're solving the current time step, you're passing that to the lagged cells, and then you're solving the current time step based on that. And then you keep going. Basically, you keep going to reduce the error. So that's where you hope to get that convergence. So some pretty pictures on the next slide, by the way. So right. So essentially what we're doing is this, right? So in order to do that, you need to have some kind of backing store, because obviously you need to share information, input files, output files, so on and so forth, and that comms. So you need really, really super fast comms, and you need really, really super fast storage. And there's a bunch of libraries that are around. So I think if you turn around, you've got a couple on the back of your shirt, haven't you?
Oh, the MPI.
We've got MPI, OpenMP. So there's a few, right? There's a few bits and pieces around that allow you to do that sharing, right? So I think that's us talking for enough for now. He's going to do a really cool demo, and then if I've got time, I'll do a really, really average demo. So the video is in there somewhere, yeah.
In downloads?
Downloads.
Sorry.
That's the fella. He's recorded his video.
Yeah, because there's quite a few services that are used here, so I thought it's easier to just use a video. So as I mentioned on CycleCloud, the first thing we do is configure the scheduler node. It's a really fast speedrun video, so I'll just see how we go. So that's I'm on the CycleCloud interface right now. Let me just make that full screen so it can be seen. What I'm doing now is setting up a scheduler node, which will control all the other worker nodes. So that it's essentially a VM. So that's what's happening. There's just configuring the VM, setting up the security groups, and configuring the software. You can set this VM however you want. So it should just take a second. It really takes like a minute or so, but it's sped. So now that the VM is up, I would then SSH onto the scheduler node, and for that, obviously get the SSH key and go into on my local machine. And
it's very clear though, you can't SSH on the stadium Wi-Fi.
And mine is recorded, so I didn't have that issue.
You won't be able to do that.
Yes.
That's why it's good to have a video.
Yep. So I'm now into the scheduler node, and here's where we use Slurm to do this kind of to submit jobs. So that's not super visible, but I can talk to it. So Slurm sets up different partitions. So if you want to run your jobs on GPU, there's a GPU partition. If you want to run your jobs on MPI-based compute, there's a partition for that. And non-MPI compute, there's also a partition for that. So it depends on what you want to use. This is a command that I've put to actually send a job to Slurm. And so job is sent, it's job number 5, and then this command just shows that the job is actually running. I'm now back to the user interface, and immediately you can see 100 nodes have been, 50 nodes have been spinning up. So I didn't have to orchestrate that. The template and CycleCloud does that. And so that takes a couple of minutes, and then once that's spun up, the job would automatically run. So that is happening now, and configured, and speed up a bit. And all done, and it's running.
Got loads of time.
Okay, cool.
Loads of time. Talk slower.
Okay, good to know I have got it. So that's done. Now it's a job monitoring. So my job is running. How do I monitor my job? So that's just to show that the job is running. And SQ to check the time, just make sure that to check the time, because you need to switch between the CLI and the actual web page. So you can actually get into the individual worker nodes. Suppose you want to see the performance, so you want to see the CPU usage, you want to see the disk bandwidth, the network bandwidth. You can monitor each of those 50 nodes, which is what I'm doing here. And these are the output files. So what's happening now is that all these nodes are running, doing my job, and there's a shared attached storage, and all the output is being put into this one shared storage. And I've named it such that each output has the folder is named via each output. So if I stream the contents of one of the outputs, you can see that the job is, I can get the data as it's coming in. If I change to another node, this is now node number 80, these are the results that are coming in, all running concurrently. Now, this job took 40 minutes, so this part is just speed running it in a couple of seconds. And the interface allows you to see the usage and also allows you to see the cost. So the cost per hour of how much the job costs you. So that's done. But the way to check that it's done would be to use Slurm again. There's an S-control command here that allows me to see status about the job. So there's a number there saying that the station is now done. There's a time, which took 40 minutes. And any other information that you need there, you can see at that point as well. So that is how you monitor the job. You can monitor it when you're SSH into the scheduler or even from the Azure Cycle Cloud web page. Now we process our results. Here, because of convenience, especially when you're looking at molecules, it's very hard to do that just by looking at terminal. So I SSH into it with VS Code, and VS Code also allows me to get certain plugins that are very useful from a chemistry standpoint. For example, there's one called Protein Builder, and what that allows me to do, it allows me to visualize the molecules. So I can actually see my reaction happening, which is transfer of a hydrogen atom from oxygen to another oxygen. So it's more chemistry there. But I can see that in situ, so I don't have to download that data. Now, if I want to see something more elaborate, I can install other software. So this is another software that allows me to see electrostatic potential. And essentially what that is how are electrons distributed on my molecule. Where do I have a lot of electrons? Where do I have a small number of electrons? So this is, if you're interested, this molecule is called dimethyl sulfoxide. It's a very good solvent, but I can do all that by looking at the data from my scheduler node. So that's the beauty of it. And automated resource deletion. Now that my job is done, I don't have to worry about turning the VMs off because the Cycle Cloud manages that. Because there's no job running, you can see that my worker nodes begin to terminate, all 100 of them, and I'll just be left with my scheduler node. And this is one of the ways that you would manage costs when it comes to using Azure Cycle Cloud. And that is a typical process that we do in a supercomputer, and I can replicate the entire process on using Azure Cycle Cloud. And that is my demo.
Cool. Thank you. My turn. Nowhere near as fun and exciting as that one. So, it's probably a little small. Hopefully you can see that a little bit better. But so this is a folder that's got a bunch of tutorials in it. So I just basically decided I'd just write one of them. This is looking like it's needing to reconnect. Just one second. So whilst it's doing that, so I think the key thing there is oh yeah, look at that, terrific. As Victor was alluding to, the idea behind all of these sort of solutions really is about creating or using the cloud to distribute your workload across multiple nodes and then bringing that all back together. So with Batch, which is the thing that I've used in the past, I've never used Cycle Cloud, but between the two of us, we kind of went, well, this is a really interesting presentation. I've seen some smiling faces, so I assume that there's at least 3 or 4 of you also think it's interesting. So that's good. So I think the key thing there really is, again, it's about how you distribute your workloads. So the power of cloud computing gives us that opportunity to scale. Batch has an auto-scale mechanism. You can auto-scale via time or processor and so on and so forth. Just runs a little, essentially a little templated job that allows you to scale things out. Come on, he says. That's, oh, here we go. Right, so I just got to log back in. All right, so the key thing here really is that what I'm not going to show, because frankly, it's it takes a lot of time to set back up, is running MPI, so that interface that allows you to do various things. If you download OpenFOAM, like I say, it's free, it runs on Windows, it runs on Unix, all the flavors of Unix pretty much, or Linux rather. There's a bunch of scenarios in there that you can just run, right, and they will just run, right, so, yep, cool, right, with that. Right, so if I was to do this, right, so you can see there's a bunch of folders. Well, maybe you can sort of see them. There's one called 0, one called constant, and one called system. That's where we've got our input files, right? So things like the grid and the geometry, the solver that we're going to use, and so on and so forth. I won't go into those in the interest of the 4 minutes that we've got left. What I will do is just run the job. This is a very small one, so it doesn't take very long. In fact, so that diagram, those 3 pictures that you saw on my slide, that's this particular scenario, and you can see that's finished. So if I now go and start the post-processor, just very quickly, so we can have a look at that. Essentially, what's happened is it's produced those output files. Right, now, if this was a different scenario and I was just using the compute power of batch, essentially I'd probably download these to somewhere else. But because I'm doing it on here, it's just easier. So if I just turn on this particular layer here, so that's the geometry. You can see the geometry there. If I turn on, just say, for instance, velocity, right? So that looks all very uninteresting. That's because that's the first time slice. I can actually play through the time slices here. There's only 3 time slices as a really simple solution. And you can see that it just plays out those time slices, right? So you can see that that's basically the same diagram at the end there that I had on that slide. So essentially, what that does very, very quickly in about 1.5 minutes, I thought Victor's presentations of his demo was going to take a little bit longer. Otherwise, I'd done a much more complex one. No, probably wouldn't have done, maybe. But the idea being, of course, is that follows that same workflow that was traditionally in the old days of big supercomputers and my Unix workstation. Input files, process, output files, and post-processing. So I think that's probably enough of demos. We do have a little bit of time for a Q&A. I think we've got 2 minutes. Yeah, 2 minutes. So if anybody's got any questions, please don't ask me to try and describe the Navier-Stokes equations. You saw the date on there. That was 1995. That was 30 years ago that I did any of this stuff. I kind of vaguely remember it, but that's why I use tools, right? Because they're there, right? So,
yes.
Yeah. So the very typical scenario, which that kind of tried to model to a degree, is called a forced cavity, and it's one of the test scenarios for almost every CFD code. So you have 3 walls and a speed going across the top, and it generates a vortex, of course, right? That's what you'd expect it to do, right? So if you can imagine that you were breaking that up, at the top of those, so that yellow and blue one, I think they were, at the top one, the boundary condition across the top would be the velocity, right? And one side would be bounded, because it's a wall, and the others would be based on the solution of that part of the domain. After time slice 1, you pass some information from what you got in that edge, those 2 edges, to the other domain, right? And then it uses that as its boundary condition. Essentially the boundary conditions of those 2 edges that are meeting each other. It uses that as the boundary conditions for the next slice, time slice.
Yeah. Do you put some thought into the design of your jobs so that they fail fast when you're developing them, to get output quickly to see if you screwed something up? Or...
I wish it was that simple. It genuinely isn't that simple. No, it's not. So the problem with any sort of, so Navier-Stokes equations, Schrodinger's the same, right? They're much higher order. They're like higher order partial differential equations. You can't solve them natively. You can kind of solve the basic Navier-Stokes equations algebraically, but you need very, very complex computational models to solve them. What you're trying to do is every time you do a calculation, you work out its value compared to its neighbors, and you work out whether things are getting closer, so that everything is moving in the same direction. And essentially what you're trying to do is minimize that error. So you tell it what is an acceptable error, and at some point it'll get to a point where you go, it's acceptable, and that's all good. But at some point, one of the cells can just go random, right? Can go completely rogue, and that can then generate itself out across the entire domain. So yeah, unfortunately, I mean, like I say, that 4 weeks was what it took to run the model to completion. But very often you'd have 2 weeks where it'd be going okay. I changed some chemical setup because it was running. Basically, I did light bulbs. It's terribly fascinating. Halogen light bulbs, because that extends the life of the tungsten because of the reaction mechanism that's involved.
Just a small add to that.
Yeah.
You can also, if it's a scientific, like for example, the complex equation, you can use lighter, less accurate methods.
Yeah.
And that's something that we do quite often. It's so light you can even run it on your local machine. And so you can get an idea of whether it'll work or not before you send it back to either cloud or a supercomputer.
Yeah, I mean, the samples on here are quite low, and OpenFOAM has quite low fidelity. I mean, my domain had like 60,000 cells. So I couldn't use MPI because MPI wasn't really a thing in those days. So that's why it took 4 weeks to run. But yeah, I mean, in an ideal scenario, you'd fail fast, but it's not really that simple because you need the actual overall answer, right? So, any more? What else here? Oh, yes, one more.
Notice in some of the demos you had about 50 nodes, and I think they had 2 CPUs each. These days, of course, you can get single physical machines that have like 128, 192 CPU cores.
Yeah.
Is that something that you go for because you sort of get the efficiency of there's a lot less messaging between machines when you have bigger machines, like fewer bigger machines as opposed to more smaller machines, or do you still prefer to go for small instance sizes?
Yeah, so the former is right. You would go for the bigger ones. One is communication, because not all nodes, so that one they did was for demo purposes, but not all nodes are enabled with MPI. So only the really, like the 192 core ones have MPI, and for the kind of work we're doing, CFD and molecular modeling, those are the most suitable for it. Yeah. So for example, if I use Azure, they've done this kind of super InfiniBand networking only for the big cores, not the tiny ones. So you almost have to use that if you're trying to do tightly coupled workloads, which is the things we're using. So yes, you're right.
Yeah, I mean, it's the same as anything else. It's a fairly simple equation, right? If you've got 192 processors, you can distribute it out to wherever you like. If you're using the bus that's actually part of the processor to shuffle information around, it's going to be much quicker than a network. Yeah. Yeah. Okay.